We're going to take a look at the idea of these multi-segment numerical integration methods. And these are the ones that you probably remember from integral calculus, the midpoint rule, the trapezoidal rule, Simpsons rule, if you've taken that. If not, no big deal. We're going to go through how we go through and work these composite sorts of integration methods. But instead of just utilizing a single shape, such as a single trapezoid or a single rectangle, we're going to subdivide into n regions. And what we're going to do is we're just going to go ahead and find the area of each of those regions and add them up. And so obviously, the more regions we get, the less of the overlap or the underlap or overlap of error we're going to get with this. So it's usually better if we can get more subdivisions, but then again, that means we're going to have to do more work. So one of the most basic types is the midpoint rule, in which we're going to find the length and the height of each of these rectangles, and we're going to use the midpoint as the point on the function. And what that tries to do is it tries to limit the overestimate and the underestimate that's usually caused by left and right endpoint estimates of these rectangles. So the distance between each of the rectangles is going to be the h, which is b minus a over n, and the height is just the function at the value. So what we can do is we can take each of those bases, which is h, and x sub is the midpoint, and we can just evaluate at each of the midpoint. So we have base times height, and we get an estimate of the area under the curve, which would help us to approximate the value of the integral. Another way that we can try to utilize areas to evaluate these integrals is the trapezoidal rule. The trapezoid's a little bit more conducive to functions with more curves in them, just because, as you can see, the trapezoid uses a line to kind of estimate the slopes at those points, and it could be an overestimate or underestimate depending upon how many rectangles you're using, or excuse me, how many trapezoids you're using, and also the slope at that point. Now, the area of our trapezoid is going to be our average of the two heights times the base. So again, we have the base h, which is going to be the b minus a over n. So base times the average of the two heights. So height 1 plus height 2 divided by 2. And we're just going to add all those up. And I want you to notice that in each of these trapezoids, the interior trapezoid sides are being used twice. So for instance, this trapezoid uses x1 once, and then the next trapezoid uses x1 as well. And then the same with x2, x3. And so all of the sides are being used twice, so we could just double each of those. And then the left end and the right end are only being used once. And so what we get is we get b minus a over 2n, the 2 coming from right here. B minus a over n is going to be the change in each of the positions. And then finally, we just go through and put it into this formula where we're adding up twice all of the heights for each side of the trapezoid, and then the left end and the right end. All right. Now, the Simpsons rule is going to utilize parabolas rather than trapezoids or rectangles. And you might remember seeing the b minus a over 3n in the Simpsons 1/3 rule. Now, the tricky part with Simpsons is that it's not necessarily a pattern of just twos, there's fours and twos. And usually the pattern that we follow is that we have f at x naught plus 4f of x1 plus 2f at x2 plus 4f x3 plus 2f x4, and we just keep doing that. And I want you to notice that, and by the way, that just keeps going until you get to f of xn. And I want you to notice that each of the odd indexes have a coefficient of 4. Each of the even indexes, this is a 4, is going to have a coefficient of 2. So that can be useful to us if we can start out with the odd index. We can multiply those by 4 and then just use every other one. And then if we can start out with an even index and use every other one, we can multiply it by 2. And we're basically going to use a division into cases when we tackle this. And so our goal is to be able to write MATLAB algorithms that are going to compute both the trapezoidal rule as well as Simpsons rule. I'm sorry, the midpoint rule as well as the Simpsons rule. And I'm going to leave you to work the trapezoidal rule as an assignment problem. So what we're going to do is we're going to first prompt the user for the input, the lower bound, the upper bound, the function, and then the subdivisions. We'll find the actual value, and then we'll write a loop that finds the midpoint rule, right, which should be pretty easy. All we have to do is just find the midpoints of each of those. And then we're going to find the percent error, and then we're going to just print out the approximate value, the midpoint value, and the percent error so we can see how close we are with this. And before we get to this one, just to kind of generate the algorithm, what I usually do is I just go ahead and graph a really simplistic function and break it up just to kind of get an idea into maybe 4 or 8 subdivisions. So let's say we have a function here, all right, and I'm just going to use some real values. So let's call this 4, let's call this 8, and let's just break it up into 4 partitions. All right, and I know they should be equal, so I apologize. I know they're not equal, so this would be 5, 6, 7. And to get the midpoint, well, what we could do is we could just say, okay, well, I'm just going to take, we know that the delta in this case, or this would be h, is going to be 1. And so what we could do is we could just start out with 4.5, and we could just add 1. So to get to here, we add 1, and to get to here, we add 1, and to get to here, we add 1. And we're going to end up stopping when we're a half less, because this is 8 minus 1/2. All right. So that's the algorithm that we're going to use. That's really our delta over 2. Right. So right here, this is really just going to be 4 plus delta over 2. And that's the algorithm that we're going to use to be able to program this in MATLAB. And that can be helpful when you're trying to write these sorts of codes, is just to sketch it out and to kind of get an idea of how the program would work. All right, so going to our MATLAB code, let's go ahead and get the input first. And so I'm going to define a sims variable for f and for x. And I'm going to let f be equal to the input where somebody enters a function. And then we're going to get the lower bound. So we're going to enter the lower bound. And the good news is we can just cheat and steal this code, and we can just copy and paste it and get the upper bound. So I'm just going to call this B, and I'm going to call this the upper bound. And then I'm going to get the number of subdivisions N. Okay, so we're going to input all right. So that takes care of the input. And now what we're going to do is we're going to go ahead and we're going to get the actual value as well as the delta. So I'm just going to call the delta. It's really h. If you want to call it h, that's fine. So delta is going to be equal to b minus a divided by n. And we're also going to get the actual value. So the actual is going to be the integral of f with respect to x from a to b. All right. So we've actually done already, if we look at the instructions, we've worked through part 1, we got all this stuff, and then we got the actual value. Now what we have to do is we have to get the actual estimated. So we're going to use a for loop, and I'm going to be sneaky about this. Remember in our picture, we started out with, and I erased the picture, but we started out with the idea that we could go through and we could just add half of delta. So I'm going to say for I equals a plus delta over 2. And then I'm going to go in increments of delta, right? Because delta doesn't have to be 1 necessarily, all right? And then I'm going to end up with b minus delta over 2. All right, so as soon as I get there, I know I'm going to stop. All right, so you have to be sneaky a little bit when you're doing these sorts of algorithms. And again, what I would suggest is just drawing out a picture, maybe making 4 or 8 partitions and just seeing, okay, what do I have to do to get to the next delta? What do I have to do to start with delta? What do I have to do to end with delta? Right? I'm going to set up another variable. I'm going to call this mid-est, like mid-estimate, and I'm going to set that equal to 0. And what I want to say is that mid-est is going to be equal to the former mid-est, all right, plus, and now here's where we're going to substitute. So I'm going to substitute into f. The old value is x, and the new value is I. Right? And so think about this. We're starting at the midpoint, a plus delta over 2, because delta is the change, but you only want to go half that way up from a. So that's what this is. And then we just keep going up by 1 or 2 or 3. And then this gives us the mid-estimate. Right? And then we're going to end. Right? And this is literally all we have to do to be able to get the midpoint sum. Right? Now, the question is, how good of a sum is this? All right. So what we're going to say is that we're going to get the error. So I'm going to call it mid-error. And that's going to be equal to the absolute value of mid-est minus actual divided by actual. All right. And then it asks us to be able to print out. So we're going to do an fprintf. And we are going to print out the actual value. Okay, so that's going to be the %f. And then we're going to print out the midpoint. So I'm going to call it the mid-estimate, or maybe we'll just call it the midpoint estimate. And that's going to be another %f. And then finally, we're going to get the %error. And I should multiply this by 100 to get the %error. I frequently do that. And that's going to be another %f. All right. And the parameters that we're calling are going to be the actual, mid-est, and mid-error. All right, so let's see what we get out of this. All right, now I'm going to use a relatively easy function so that way we can test it. So let's just use something really basic. Let's say 3x squared. All right, and we know that if we use 3x squared, we're going to cube it. So we're just going to take the lower bound cubed and subtract it from the upper bound cubed, and that makes it really easy. So let's say the lower bound is going to be something like, I don't know, like 5, and let's say the upper bound is 1. So we know 5 cubed is going to be 125, and 1 cubed is 1. So we should end up with like around 124 when we do this. Now let's use a pretty elementary number of subdivisions, like 8. All right, so now this one gives us negative 124, which is the actual value, and then we have this midpoint estimate, which is way off. Excuse me. So there might be something wrong here, or it might not be. Maybe the value is just too large. Concerning that we got this negative value for the integral, but regardless, oh, that's because I put the lower in first in the upper bound, so that does make sense. All right, so let's try it again. Let's just use a smaller value. Let's say x squared, and let's say the lower bound is 1. Let's say the upper bound is 3, and let's use 8 subdivisions. All right, so once again, we get a really big midpoint estimate. All right, and that's not all that good. We certainly want something that's a little bit closer. All right, and I think I remember why. I think it's because I never multiplied up here by delta. Right. So what this does is this just finds the height. I think I forgot to multiply by the base right here. Okay, so that would have been helpful. So let's try it again. So let's try x squared. Let's go from 1 to 3, and let's just do 8 subdivisions. All right, there we go. So this is a really good approximation just using 8 subdivisions. All right, now, of course, if we use more subdivisions, we'll get even closer to the precise answer. So let's just do x squared, and let's do 0 to 3, and let's use something like 1,000 subdivisions. And it might take a minute or two for it to compute, but it's not that big of a deal. So we'll just give it a moment to compute. And notice the % error is really, really, really small. All right, and that's just because we use so many of these. And even though it takes longer to compute, it's a little bit more powerful as you increase n than it was some of those Newton code algorithms. All right. So in the next video, what I'm going to do is I'm going to program the Simpsons rule, the 1/3 Simpsons rule, and then we're going to take a look at a specific type of problem where we could apply this to.